Hello, we shall continue our discussion on wide area networks. In the last lecture, we have discussed the basic model of wide area network, which is referred to as switched communication network. And we have seen that it comprises nodes and stations. Stations are equipments which sends data or end user equipments, and you have got a collection of nodes, and nodes are essentially switches. And we have introduced circuit switching, one of the most important technique, dominant technique used in wide area networking, with its best known example, the public telephone network. We have discussed the advantages and drawbacks of this circuit switching technique. To overcome some of the drawbacks, we introduced another switching technique known as message switching. But we have seen that the message switching has some advantages but some disadvantages as well. To get best of both the worlds, we shall introduce another technique known as packet switching. Let us see what is the concept, how it works, and then we shall compare the three techniques: circuit switching, message switching, and packet switching. Let's now consider the packet switching. We have a message to be sent. It can be a long message. What we do, we break it up into small packets of some maximum size, and each of these packets is provided with some metadata, header and trailer. So here you have got header and there you have got trailer. This middle part is called the payload, which is essentially the data that you are sending. On the other hand, header and trailer, which is called metadata, this metadata is added as an additional information. The additional information can be source address, destination address, then your data length, and sequence number, etc. The trailer is usually provided with frame check sequence, which is used for the purpose of error detection. Earlier we have discussed in detail how error detection can be done by using cyclic redundancy code, and we have seen a frame check sequence is appended with the data to facilitate error detection. This is what is being done here. And with the help of this metadata comprising header and trailer, many operations can be done, like routing, flow control, congestion control, and so on. So this introduction of this metadata is a very fundamental innovative concept fundamental innovative concept of networking technology. And with the help of this metadata, each packet is made self-descriptive. Moreover, we shall use the same basic concept of store and forward. First thing that we are doing is breaking down a long message into a number of packets. So this is again another packet with header and trailer and so on. Now let us see how the packet switching works. We have the stations like A, B. As you have seen in any switched communication network, then you have a number of nodes which are switches. In this case, each of these nodes is a packet switching node, PS, packet switching node, PS, and they are interconnected in some form. So station A is connected to packet switch 1, station B is connected to packet switch, let's assume this is 2 and 3, and this is 4. And like message switching nodes, here also each node is provided with storage facility. Storage facility because we use the same basic concept of message switching, store and forward. This is also a very important concept by which cost of the link can be reduced. The cost of circuit switch link, which is a dedicated link to be established before you can send data, that can be avoided. And because of that, the store and forward helps you to reduce the cost of the path, cost of establishing a link. Now, this is the basic configuration. Let us look at the time sequence diagram. Time sequence diagram. There are two basic approaches. First one is known as datagram. Datagram packet switching. In this case, let's assume we have, as usual, 4 nodes through which communication is taking place. Just like message switching, here there is no call setup time. That means there is no need for call request, call acknowledge or anything of that kind. We are starting to send packets straight away. Packet number 1 followed by packet number 2 followed by packet number 3. So this is 1, 2, 3. There can be some gap in between or it can be sent immediately. So this is from node 1 to node 2. By the time you are sending packet 2 from 1 to 2, node 2 can send packet 1 from node 2 to node 3. And by the time when you are sending packet 3 from node 1 to 2, you can send packet 2 which has been already received by node 2 from node 2 to node 3. So in this way, the packets are sent in store and forward manner. Here you will get packet 1 followed by packet 2 followed by packet 3. So communication is here using 4 nodes. Now what are the key features here? First of all, no call setup time. This is one of the most important features. And each packet is independent. That means packet 1 may be passing through from may follow the route 1, 2, 3 and 4, but packet 2 may not be sent through the same route because the different paths, the same paths may not be followed. Each packet is self-descriptive. So the nodes are able to can do routing. Nodes are provided with the capability of routing. It is essential in datagram packet switching technique of the nodes which are doing datagram packet switching. And because nodes are more powerful, this approach is inherently more flexible and powerful. There is another approach which is known as virtual circuit packet switching. In this case, assuming the same phone number of nodes between 2 stations, here, like circuit switching, here you are initially performing call setup by sending call request packet. So you will send call request packet from 1 to 2, then 2 to 3 and then 3 to 4. In this way you will send the call request packet. In response, call acknowledge packet will be sent from the other end, and a path is established. Here we see it is not really a dedicated link. Even in the return path, these are small packets known as call acknowledge packets, which are sent in the same basic approach of store and forward. That's why there is some delay in between, as you can notice. And after the path is established, all the packets of a message can be sent through the same route. So you will send packet 1, packet 2, packet 3. There is no delay as such in between. You can send immediately 1, 2, 3, and then by the time 2 goes, 1 will go from 2 to 3, then 1 will go from 3 to 4, and this is your 2, then 3 can come here, 2 and 3. There can be some delay between each of these packets, but the packets will receive in order delivery. Because the same path is being followed, you are able to deliver in the same order in which you are sending. That may not be true in your datagram packet switching. Since the packets are sent through different routes, the delay through different routes can be different. As a consequence, ultimately the sequence at which the packets are received in the destination node, the packets may be out of order. So here it can be out of order. If you are lucky, you will receive in order, but there is a possibility of receiving out of order, which cannot happen in case of your virtual circuit packet switching, because it is functioning like circuit switching. But remember, it is not circuit switching, exactly circuit switching, because again the same store and forward approach is used, and there is variable amount of delay between the receipt of each of these packets. So there can be some delay between the receipt of between say packet 1, then there can be some delay before you receive packet 2, or after receiving 2 there can be some delay before you receive packet 3, but you will receive in order. So there can be variable delay. Now, here the nodes are not provided with the capability of routing, because routing is done by the source node in the beginning and a virtual path is set up. That's why it is called virtual circuit. And because of this, it is more in this particular approach, it is more difficult to adopt to congestion. Whenever the number of packets in a network increases, it becomes problematic. There may be more error, there can be lots of retransmission, and a particular path may be very much congested. In such a case, it may be necessary to route a packet through another path, which cannot be done in this virtual circuit packet switching, but that can be easily implemented in datagram type packet switching, which we have discussed earlier. Now let us consider another important technique, another important parameter, that is packet size. We have seen that basic difference between message switching and packet switching is you are breaking down a long message into a number of small packets of some maximum size. Now, how small? That is the question. It has been found that transmission time reduces with packet size. That means as you make the packet size small, you will require lesser time. On the other hand, if you are sending a long message, the transmission time will be more. But there is a limit to it. Whenever the packet size or the payload part, the data part becomes comparable with the metadata part, the control information, then you will lose the advantage of the smaller packet size. So we can plot it in this way. Suppose this is in this direction your packet size. And here say transmission time. So when the packet size is large, transmission time is more. As you reduce the packet size, then transmission time reduces. But up to some limit, the transmission time, when the size of the packet, the payload part, becomes comparable with the control part, then the transmission time will again increase. So there is some kind of minimum here. So you have to choose the packet size judiciously, or the maximum packet size judiciously, so that you can efficiently transfer. That means the transmission time is small. Now, to obtain the performance of a network, you have to look at three important characteristics: propagation delay, propagation delay is dependent on the transmission delay, that means delay through the guided media. In this case, if you are using guided media, then we know that the speed of electromagnetic signal through guided media is 2 into 10 to the power 8 meter per second. So depending on the length of the communication path, delay will be decided, and this is the speed of the electromagnetic signal, and that will decide the propagation delay. On the other hand, the transmission time will be decided at what rate you are transmitting and whether you are able to transfer in parallel. Here, in both in virtual circuit and in datagram packet switching, we can see that if we look at this particular time frame, we will find that, say, from node 1 to 2, packet 3 is being transmitted. During the same period, packet 2 is transmitted from 2 to 3, and packet 1 is being transmitted from 3 to 4. So we find that different parts of the same message are being transmitted simultaneously, and as a consequence, the transmission time will be small in packet switching. Then there is another important parameter, is the node delay. Each node will require some time to process the data, to perform different functions based on the metadata that has been received, like routing, error detection, and so on. So, and also depending on the length of the queue, how many packets have already been accumulated, there will be some delay, and that decides the node delay. And these three parameters will decide how efficiently you can do data communication through a packet switching network. Now, let us compare the circuit switching and the two types of packet switching that we have discussed right now. As you have seen, in circuit switching, a dedicated path is established from source node to the destination node, which is not necessary in datagram type packet switching or virtual circuit type packet switching. Then, after the path is set up in circuit switching network, you can send continuously, because as if a pipe has been established and transparently, without delay, you can send it from source node to destination node, continuous data, which cannot be done in packet switching. There is some node delay and you are sending in terms of packets. And since there is no delay in circuit switching, it is you can achieve it is the data transmission is fast, and you can use it for interactive applications. On the other hand, the message switching, where the packets can be arbitrarily long, message can be very long. The delay is unpredictable and not suitable for interactive traffic. On the other hand, in packet switching, we are able to overcome that problem by reducing the size of the message, and both datagram type and virtual circuit type are fast and can be used for interactive traffic. In circuit switching, one advantage is that the nodes need not have storage facility, because you are sending from source node to destination node. There is no need to store in between. On the other hand, you require storage facility both in datagram packet switching and in virtual circuit packet switching. And circuit switching has call setup delay, as we have seen, but the datagram and virtual circuit type packet switching have packet transmission delay in both the cases. Then in case of circuit switching, when there is overload, you have got large number of packets to be sent, it may block the call setup. If you don't get a path, then you will not be able to establish a link, as you have seen while discussing circuit switching. In case of packet switching, in case of datagram type packet switching, overload increases packet delay. Only problem that can arise here, in any case, the packets can be sent, but there will be some delay, and delay will increase as the load increases. On the other hand, in virtual circuit type packet switching, overload may block the call setup, as well as that it can have the packet delay, variable delay, as the load increases. In circuit switching, there is no need for speed or code conversion. From one end to the other end, you are transmitting at the same speed without any code conversion. On the other hand, in say your datagram packet switching, from node 1 to node 2, you may be transmitting in one speed, but from node 2 to node 3, depending on the type of link you are using, you can use different speed, different technology, so it may be necessary to do code conversion. So is true for virtual circuit type packet switching. So speed and code conversion may be used in packet switching. And circuit switching gives you fixed bandwidth from source to destination. On the other hand, the bandwidth can be dynamically changed in packet switching, both datagram type and virtual circuit type, depending on the link you are using. And circuit switching has no overhead after the call setup, but datagram type and virtual circuit type packet switching both have overhead bit in each packet. As you have seen, that metadata that is being added is the overhead, and that is present in both datagram type and virtual circuit packet switching. So we have seen the advantages and disadvantages, but overall packet switching is very advantageous, and that is the reason why it is widely used nowadays. Now let us consider a popular protocol known as X.25. It is the best known and widely used protocol, and it is used for interfacing to a packet switch network. That means an user node can interface to a packet switch network using this X.25 protocol. Let us see the basic features of it. So it specifies the interface between the host system and the packet switching network. The protocol has 3 layers. It has got 3 layers. These 3 layers are physical layer, link layer, and packet layer. These 3 layers correspond to the lower 3 layers of the OSI model. We have earlier discussed the OSI model, OSI 7-layer model, where we have seen there are 7 layers, 1, 2, 3, 4, 5, 6 and 7. These 7, out of these 7 layers, the lower 3 layers concerns with communication purposes, and the physical layer of this and OSI model correspond to the physical layer of the X.25 protocol. The link layer correspond to the data link layer, and the packet layer correspond to the network layer. So let us briefly discuss these 3 layers one after the other. First, let us consider the physical layer. The physical layer specifies the physical, electrical, and procedural interface for interfacing to X.25 network, and the protocol that is being specified is known as X.21. Unfortunately, X.25 is not widely used, or in fact it is rarely used, because it requires digital signaling. And as an interim measure, until all the nodes of the stations are capable of providing digital signaling, somewhat similar to RS-232's protocol is used. So somewhat similar to RS-232 was defined, and this is widely used. And in RS-232C, as you know, analog signaling is used. We have already discussed in detail the RS-232C, and we have seen the physical, electrical, functional and procedural components in it. So here somewhat similar things are specified. We are not going to the details of it. Let us go to the second layer, which is known as the link layer. And link layer is, as you know, it corresponds to the data link layer, of the OSI model. And as we know, the physical layer is concerns with transmission of bits, and it is the responsibility of the data link layer to achieve reliable communication utilizing the physical layer, and that is precisely what is being done by the link layer. So it concerns with reliable communication across the physical link by transmitting data as a sequence of frames. So it sends as a sequence of frames. And as we know, whenever a frame is constructed, we shall discuss in little bit detail, header and tailer is introduced to facilitate or to implement reliability, to incorporate reliability. We can look at this from this using this diagram. We can explain how it really works. Suppose this is the user data which has to be sent through a packet switching network. The layer 3 adds one header which is done by the X.25 packet layer. Then this is sent to this link layer. Link layer adds what is known as LAP, link access protocol balanced header, here, and link access protocol balanced trailer at the end, and this packet is being sent. This is very similar to the way this is being done, and this particular data link layer uses the entire packet as a payload, and it is based on the subset of HDLC frame format. The frame format that is being used is very similar to HDLC. So let us explain the frame format of HDLC. It has got flag bit for synchronous communication, 0 followed by 6 ones, then a 0, 8 bit. After this there is an address part which can be 8 bit. Then there is control part which is 8 bit once again. Then you have data up to some size, maximum size. Then you have the frame check sequence which is 16 bit. Then you have the same flag, 0 followed by 6 ones and a 0. This is how the framing is being done. Now there is one problem in this particular case. You see, you have sent a flag of 8 bit in the beginning and at the end to identify the beginning and end of a frame. Now suppose the same sequence appears as part of data or control bit or address, whatever it may be. How do you differentiate between a flag and data part or the payload part which is provided by the packet layer? This can be done by using a concept known as bit stuffing. this is done by using a concept known as bit stuffing. Idea is, after this flag of 8 bit, if you get a sequence of 5 zeros, you introduce a 5 ones, you introduce a 0. Introduce 0 after each 5 ones. So this sequence will never arise. That is how you can avoid the occurrence of flag in this part of the frame. Now let us come to the packet layer. What this packet layer does, it deals with addressing, flow control, and establishes virtual circuits. To establish a virtual circuit, as you know, you have to follow a sequence like call request, then call indication, call request. The other side will send, suppose this is the call request packet sent, the other side will get a response known as incoming call, and then it will give indication this is the network and this is the other end, and in this gate you will get the incoming call, then it will get the call accepted, packet is being sent, and that is being sent, and the other side will get the call indication, and after this way the call is set up, it will perform data transfer. It will send data, and on this side you will get data. The other side may also send data, and it will be received as data, and then it will be terminated by clear request by sending another packet, and there will be an indication on that side, clear indication, and so on. So, and this is how we will do call setup, data transfer, and then clearing of the network, circuit establishment. And there are two types of services. One is known as switched virtual circuit, in which you will do these three phases: call establishment, data transfer, and call clearance. But there is another type of service where you have permanent virtual circuit, like lease line. So lease line is a dedicated path already available to you, which can be also used for packet switching. In such a case, this call setup and call clearance, these two parts are not necessary. You will send data packets, there will be data indication on the other side, and so on. So this is how data transfer can take place. Now you can do multiplexing. You can have at most 4095 simultaneous virtual circuits through the same link simultaneously. So this is an advantage of virtual circuit network, packet switch network, where you can have multiplexing. A number of virtual circuits can be simultaneously established. Before I conclude, let me tell about another important function, that is XXX protocol. Although this X.25 protocol was proposed long back, sometime in 1976, then it has been enhanced several times, but this particular facility may not be present in all the user nodes. For example, dump nodes or unintelligent nodes, or rather stations. In such a case, what will you do? For that purpose, this protocol XXX has been provided, which comprises of X.X.3, which provides you the pad parameters, PAD stands for packet assembly and disassembly. That means here is your station, then you will install PAD, packet assembly and disassembly. This will link to your this circuit switch network. Another protocol is used, X.28, which provides you terminal to PAD interface protocol. PAD interface, which is equivalent to DT to PAD, you can say, data terminal equipment to PAD, which is the end user equipment. And finally, X.29, which is for the protocol between PAD and the network. So friends, we have discussed the fundamental concepts of packet switching with an example, X.25, which provides the interface to the packet switch network. Thank you.